start our webinar today from brief introduction. We'll hope that today everything will work fine as expected, but who knows? Again, it's Jan Richardson, who is research scientist at the Department of Astronomy, University of Maryland, and the Heliophysics Division, NASA Goddard Space Flight Center, Greenfield, Maryland. He got his degrees from Imperial College in London. His research interests include solar energetic particles, cosmic rays, geomagnetic storms, and solar wind structures. And he is a compiler with Hilary Canne, University of Tasmania, of a widely used interplanetary coronal mass ejection catalog. He is elected American Geophysical Union Secretary for Solar and Heliospheric Physics for 2010 to 2014, and received AGO Editor Citation and Excellence in Refereeing 6 times. So please go ahead. You have 40 minutes. You have presenters, right? So please go ahead.
Okay, thank you. First of all, I have to share my screen, don't I? Apologies for those who tuned in a couple of weeks ago. My computer did Windows updates. Just as I started the presentation and I couldn't get out of it. So I got a new computer last week, and I was going to use that nice NASA computer, and it failed overnight. It's not charging up. I can't get it started this morning, so we're back to the computer that failed me a couple of weeks ago, and we'll see what happens. So just keep your fingers crossed. Okay, right. So I collect my thoughts because it's been a bit hectic this morning. Okay, so solar energetic particles observed by the stereo spacecraft during solar cycle 24. This is a summary of some work that we've done. I can't review everything that's been done with stereo, but just to give you a flavor of some of the things we've done. Okay, so solar energetic. Let me see if I can find mine. Can you see my? Yeah, there was probably was a mute on there. Okay.
We can see both screen and your mouse.
I can see the hand. Okay, right.
Yeah.
So solar energetic particles are temporary enhancements in the proton, heavy ion, and electron intensity resulting from the acceleration of particles by solar flares or shocks accelerated by, driven by coronal mass ejections, and their subsequent release and particle transport through the heliosphere. They range in energy from tens of keVs to GeVs. There's significant hazard to space-based assets, in particular outside the shield of Earth's magnetosphere and aircraft at high latitudes. And part of the problem is they occur fairly randomly without little warning, and the fastest particles can arrive at Earth's orbit within minutes of the solar event. Now there's a figure on the right here. Okay, let's get rid of that. Okay, yeah. So the figure on the right shows the Bastille Day 2000 event. This is an example. This is the X-ray light curve here, and this is 2 hours of data. And here's the inject particle increase at GeV energies measured on the ground by neutron monitor. And here's the CME lifting off. So everything happens very quickly. The particles arrive. This X-ray flare occurs. The CME occurs. It's very close, very similar timing. And that's one of the challenges in understanding SEP events. Quite disentangling what's happening when. And there's three words I picked up here. There's acceleration particles. You can accelerate particles, then they've got to be released and transport, and that's really sort of 3 key elements of understanding SEPs: how they're accelerated, how they're released, and how they are transported to the observer. And okay, here we go. Oh, it's going to do it again. Here we go. Yeah, okay. Here's advanced this time. So acceleration of SCPs is a big topic in itself, and I'm not really going to discuss that because it's very controversial and there's a lot of heated debate about it. But there's basically 2 mechanisms. Okay, this just shows a flare and a sort of flux rope lifting off, reconnection below the flux rope. This thing lifts off. It drives as a CME. It drives a shock ahead of it. It's fast enough, and you also get reconnection, which can also accelerate particles. So there's basically 2 basic processes that may contribute to SCP events: flare acceleration by based by flare and by the CME. And how does the shock accelerate particles? Is it just a simple cartoon here? Here's the shock front, and the speed of one side of the shock is faster than the other, and there's turbulence. So basically, particles get scattered backwards and forwards between the upstream and downstream regions. There are more subtleties that I won't go into, and the idea is that they gain energy as they scatter backwards and forwards because the scattering centers are converging. And here's a picture of CME, and all these speckles on the picture are actually integrated particles hitting the CCD and the ASCO chronograph detector. So it shows nice, just shows how the close association between CMEs and particles. And classic picture is that there are two types of particle events. They're very short duration ones. Here's an event here, which are last a few hours to a day. They're usually called impulsive events. Actually, it's not, the original term was because they're associated with impulsive brief solar flares, rather than actually classifying the type of the SEP. Usually attributed to flare acceleration, electron rich. They have enhancement of helium-3, which is interesting. I won't go into that. It's a very strange property that somehow these acceleration processes are able to bump up helium-3 relative to the solar wind and the photosphere. They are iron rich, and they also have a lot of electrons in them. And the classic picture is they're associated with what are called type 3 radio emission. I'll come back to that later. These are fast drift radio emission associated with fast electron, with beams of electrons. The second type of event are much longer. This is there's a whole load of stuff on this picture here, but basically you've got loads of particles at various energies in here, and so this is several days, and you get the flare and the CME occurring here, and these particles last for the events last for many days, and sometimes a shock comes through. The shock is here in the solar wind data at the bottom. The solar jump in the solar wind speed, the density, and the field intensity here, and you can see how the particularly lower energies here, the SEP intensity tends to peak around the shock. There's even a little spike in there, which is interesting. So these are what are called gradual events, usually, again, because they're actually associated with long duration flares typically. And so these electron poor, they have composition rather like the solar wind, and they have they're associated with type 2 radio bursts, which is associated with the shock coming out, acceleration of the shock. But actually, they're associated with the type 3s, which is interesting because that's sort of a signature of the flare acceleration. And what are they doing in big SEP events? But anyway, there, that's an interesting puzzle. But basically, they're actually not, these two classes, they're not actually distinct. They're actually a continuum of events, and these are sort of the two extreme cases. And there are many mixed events, gradual events which show, say, they're enriched in helium-3. So that's a bit of a puzzle. It's not, anyway, but that's another part of the picture. Okay, so another aspect of ACPs is, okay, you've got this shock coming out, and the connection, there are different intensity time profiles shown here as the connection changes between the sun and the shock. So it's a Parker spiral field line when the flare and the CME are on the western hemisphere. The sun is back to front of the Earth. Bear that in mind. The west is over here on the sun. When the event is on the western hemisphere, then the particles arrive. You're well connected to the solar event. The particles arrive very rapidly, and then when the shock goes through, you're just going through the flank of the shock. So there's really not much of effect, like I showed you just now in that big event, the gradual event. If the CME is coming out from the center, then you get a fairly prompt onset, but you also see the fairly strong part of the shock coming by. So you get a peak, particularly the lower energies here, as the shock goes by. As you go to the event being on the east, you're poorly connected to the event early on, but then the shock comes by, and in fact, the intensity can actually be higher behind the shock, because then you're over here and you're connecting to the stronger parts of the shock, nearer the nose of the shock. And then there are some cases where the event is poorly connected, way off in the east, and actually the particles tend to just co-rotate around with a solar rotation into you, and you get an event that can last for many days. So this is sort of a basic picture from looking at built up from many events, looking at the different shapes of the SEP events. And so part of this is trying to understand the acceleration processes, and this is an example of how you might do that. Variation of the ion-to-oxygen ratio versus longitude of the flare, and these are on the west here, and the black ones dots mean that these are prompt events. These are when particles turn on very rapidly, and they seem to have a high ion reduction ratio versus the which may indicate that there's some component of flare acceleration. Remember, the flare particles have high induction ratios classically. So this may be a signature that when you're well connected, you see flare accelerated ions, and then other cases you're dominated by the shock accelerated ions with a more of a with lower induction ratios. So this is the thing. These pictures are built up from many events, but the idea of the stereo mission is that you have two spacecraft ahead and behind that are actually separating away from the Earth, behind and ahead of the Earth. And you could then look at the same SEP event from three locations and see whether these patterns, say in the time intensity time profile and also the interaction ratio, whether they can be seen in single events. So that was one of the motivations from SEP point of view for the stereo mission, which was launched in October 2006, and the spacecraft separate from the Earth about 2.5 degrees each year. So this just shows early in the mission. Okay. Oh, 1 point, yes. And so you're comparing the stereos with observations at Earth, and I just put a comment in why I don't use GOES data. A lot of people use GOES data, which is up here, and I like to use data from the the SOHO spacecraft, particularly EFIN and ERNI instruments, which have much lower backgrounds. Here's the background in GOES. Here's the EFIN data, and you can see, okay, in GOES people say, oh, these are all SEP events, but in fact, if you look at the other data sets, you can see there are many more events which you just don't see in GOES, and you can actually see. So it's a much better data set. I don't use GOES unless I really have to, because it's just so much more detailed than the other data sets. So bear that in mind if people are using GOES data for particle events. And the other thing is, I tend to look at 25 MeV protons. This is a very messy slide intentionally. There's loads of energy channels up here, and there's a couple of shocks, and I'm looking at SEP onsets, and here's one down here, which it's very hard to see in the lower energy channels because it's dominated by this previous event and the shock accelerated event here. So I'm looking for 25 MeV. This is actually a little bit higher, but it's these higher energies, you can really see the SEP onsets much more clearly than you can at lower energies when there's so much other things going on. So we like to use 25 MeV protons. They're also interested because they're more radiation hazard. Let's see. Actually, since 1967, we have a long list of these events. There's over 1,000 events, so we can use them for long-term studies at a similar energy. So I'm going to focus on 25 MeV proton events seen by the stereos. This shows a overview of the 40 to 24 MeV, almost 25 MeV anyway, proton intensities at stereo A at the Earth and S stereo B from the launch through to this is suspiciously like just before the AGU meeting, which is when I did the plot. So here's stereo A, stereo Earth, and stereo B. And one thing you really see, apart from this event in December 2006, the